All right, so I guess we are now live on YouTube. And before I introduce Julie, let me share my screen. So as we usually do, let me, before introducing our speaker today, let me talk about the next webinar, which is going to be 2 weeks from today, and it's going to be given by Professor Tatiana Rapoport from the Federal University of Rio, and the title will be Orbital Hall Effect in 2D Materials, and then we will go back to our usual time at 4 p.m. And today, it's a great pleasure to have Professor Julie Grollier. She's a research director at the CNRS Thales lab in France, where she joined in 2005. Her current research interests include spintronics and new devices for cognitive computation. Professor Grollier has over 100 publications, and she's a frequently invited speaker in several international conferences. She's also a fellow of the American Physical Society. She's the recipient of several prizes. In 2010, she was awarded the Jacques Herbrand Prize of the French Academy of Science. And in 2018, the Silver Medal of the CNRS for her pioneering work on spintronics and brain-inspired computing. So it's a great pleasure. Thank you, Julie, for accepting our invitation to speak here at the Condensed Matter webinar of the Brazilian Physical Society. And the screen is yours. Thank you. Let me unshare now.
Okay, thank you very much for the introduction and for the invitation. So let me share my screen. Okay, so I guess you can see my screen, right?
Yes, perfect. Yeah.
Okay. Thank you. So, oh, by the way, how do we proceed? Is it possible to ask questions during my talk or only in the end?
We usually have questions at the end.
Okay. Okay, thank you. All right, well, if something is really completely unclear, let me know. So in this talk, I would like to discuss why I believe that physics and materials are important for neuromorphic computing. So, as you know, neural networks are inspired from the brain, but today they run on computers which have an architecture completely different from the brain. And because of that, training neural network is extremely power inefficient. So today, neural networks are actually converted into some mathematical models that are heavily parameterized. So the synapses are in fact emulated by real values, some parameters called synaptic weights. And there are up to several millions or billions of these parameters. And so when you want to run or train a neural network, you need to go fetch at each computational step, you need to go fetch into the memory all these parameters and bring them to the compute where you do complex operation and put them back into memory. And the problem is that in our current digital computers, memory and compute are far apart. And the farther away is the memory from the compute, the more energy it requires to go fetch the data, as illustrated in this graph here. And so this is why today AI is consuming a huge amount of energy. So here you have some recent numbers. You see the CO2 consumption for human life for 1 year in average, and compared to the CO2 consumption to train one of the big recent networks for natural language processing. And you see that here you have more than one order of magnitude. So it's really huge. And compared to that, actually, our biological neural networks actually consume very little power, only 20 watts for our brains. And this is because in the brain, memory and compute are completely intertwined. Actually, synapses that carries memory are directly connected to the neurons that perform the compute. So memories here in situ, there are no such data transfer, and this is why our brain is so energy efficient. So today it's quite clear that we need to come back to such an architecture if we want to build electronic chips that run AI with a low energy consumption. So what we need to do is to make this kind of neural network where the circles are physical neurons interconnected by synapses. Here, these arrows. That actually, here you have some devices in between the neurons that carry some memory that they can give directly to the neurons. So we need physical neurons, we need physical synapses. So the first idea can be to make this kind of physical neural networks with our current technology, that is CMOS electronics. And if you do that, as shown in this graph here, indeed, you can gain an order of magnitude in energy compared to CPUs and GPUs. The vertical axis here is the power efficiency of learning in neural networks. Okay, the issue with using only CMOS is that actually in CMOS memory, the SRAM memories occupy a large area and they're also expensive. And so it's difficult to shrink the size of the neural network. Actually, it's complicated to fit a lot of devices in the size of a chip. So you may know that typical chips are about 1 centimeter square. And if you make the computation, the calculation, you can see that, so for example, if you want to classify image today, you need 100 million of neurons and synapses. So if you want to fit all these devices in a 1 centimeter square chip, if you make the calculation, you see that each device should be smaller than 1 micrometer square. So it means that we need nano neurons and nano synapses. And this is not possible with CMOS. You cannot shrink the size of memory to nanoscale. And so this is what is illustrated here. It shows that if we were able to complement CMOS with nanotechnologies for memories, for example, well, we can gain 2 more orders of magnitude for training efficiency and get closer to the brain. And so there is a huge effort today to do that. And why it's now becoming possible is because these emerging memory technologies have made a lot of progress in these last years, and now they can be monolithically integrated in the CMOS process. So there are different examples here. These memories, they can be spintronics, they can be based on resistive switching, filamentary switching in oxides, they can be based on phase change materials. But in all these cases, what you see, so I'm going here to focus on the spintronics, but it's the same for the other ones. Here you have a magnetic tunnel junction that is integrated in the vias that directly connect the transistors at the bottom. And so you see, you cannot be much closer to the compute, okay? And so now this is becoming mature. And so commercially, I mean, they are integrated in the foundry process, and industry has demonstrated gigabit prototypes, which means that you can put billions of such devices on a chip. So it's very interesting, of course, for neuromorphic computing. And what is interesting also is that here, these devices are just, 2-level devices, 0, 1, for memory applications. But actually, all these kind of devices, depending on the materials and physics, are very multifunctional. And in fact, they can go beyond just, storing zeros and ones. They can emulate many features of neurons and synapses. So as you may know, in the brain, synapses are analog memories, neuron spikes. These spikes can synchronize, which gives rise to brain waves, oscillations. All this is highly nonlinear, and all these processes are used for computing. And what is interesting is that these emerging nano devices and materials such as spintronics, ferroelectrics, phase change, organics, optics, and many can actually emulate all this functionality. And so one very interesting question to ask is whether we can use this physics, these effects, to speed up AI and decrease its energy consumption. So this is the topic of my talk. So if we want to do that, we need to know what are the minimal features that the physical nano device we are going to use need. So here in this talk, I'm going to focus on a branch of neuromorphic computing that really tries to emulate nano neurons and nano synapses and to emulate, let's say, the features of today's neural network models, okay? Because after all, they are state of the art. So my point of view is that if we want to make efficient neural networks on chips, we should be able to, we should aim to reach the capacities of this mathematical neural network, which are state of the art. And so in these mathematical models, the first thing is that neurons, so there are mathematical functions that take real values as input, real values are output, and the key feature is that these functions should be nonlinear. Okay, so we need to emulate at least this with our nano devices. Synapses are analog valves, so they multiply the output of the pre-neurons with a synaptic weight W. And the important information, altogether, synapses do a weighted sum on the output of neurons. You see here. And so then this goes to the neuron and then it applies the nonlinear function. Okay, so you can see synapses as analog valves with a weight that can be negative or positive. And of course, this weight should be memorized in situ by the device. So if we want to make the deep neural networks on chip, we emulate them, we need these basic features of devices. So what I would like to show in my talk is that in order to be able to do that, we need to work on different aspects. We cannot focus just on the devices, or we need to, at the same time, work on the devices, the materials, and the algorithm, so that there is an effective use of these new devices across the whole computational stack. Because the algorithm should be adapted to the devices, and the devices should be adapted to the algorithm. They cannot be independently considered. So I'm going to give some examples based on our work. And so I will first start with what we are doing in terms of neuromorphic devices and materials. So the challenge that we would like to tackle is how to densely interconnect synapses and neurons. So, of course, there is the first challenge of making nano synapses, nano neurons, and put a lot on the chip. But then you also need to be able to interconnect them very densely. In the brain, for example, in the cortex, there are 10,000 synapses per neuron. So it means 10,000 wires per neurons. Here you have a 3D reconstruction of retina. Each wire has a different color. And so it comes from a video. So actually this is 3D, right? And so you see how complex this is in the brain. In order to reach this density, you have all these wires that cross in very complex ways in 3D. And so, of course, this is very difficult to make with our current electronics. You imagine connect each neuron is connected to 10,000 other ones through synapses. It's a lot. So, so what we thought is that maybe we could minimize the number of wires if we tried to complement this wire connectivity with radio frequency communications. Because after all, we know that radio waves are very efficient to connect a large number of elements together. For example, we can all be connected through our mobile phones. And so we thought maybe we could make some kind of neural network where the neurons and the synapses communicate together through radio frequency. And so for this, we thought, well, maybe we can use spintronics actually. So how come? Well, the reason for that is that actually magnetic tunnel junction can be used, can emit microwaves and can be used as radio frequency neurons. So, as you know, a magnetic tunnel junction is a cylinder. It's a sandwich of two magnetic layers within between a thin insulator. And so when the magnetizations are parallel or anti-parallel, this can code for a 0 or 1. And this is what happens when you use them as bistable memories, binary memories, elements. But you don't need to use them in that way. Actually, if you send a current through this nanojunction, the current can get spin polarized by the first magnet, and then these spins can be transferred to the magnetization of the second layer. And when these spins are transferred, they give a spin torque to the magnetization that can start to oscillate. And because this is a magnetoresistive device, when you measure the voltage here, this is what we do, this is an experiment, you measure a signal that depends on the oscillation of the magnetization, as you can see here. Okay, and so you see that this signal oscillates at the nanoscale range. So this is a microwave signal. What is interesting is that depending on the amount of current that you put, the orbit of the magnetization is going to change because the magnetization receives different amounts of spin, right? So it's going to oscillate differently. The trajectory is going to change. And so if we send a small DC current, basically there is not going to be any emitted microwave power. But if we increase the current at some point, there is a microwave emission, and the more current you put, the larger this amplitude, so the larger the microwave power. And so you see here that if we plot the emitted microwave power as a function of the DC current, we have some kind of rectified linear unit. This shape is very reminiscent of the functions that are used today in neural networks. So if you want, you have a microwave neuron, nanoneuron, where the input is a current. The nonlinear function is here. And then the output, that is a microwave power, can be broadcasted through RF to other neurons. Now, in our experiments here, we are using devices that have a diameter of about 400 nanometer. But these devices, as you know, can be scaled down. And in that case, their power consumption can be down to microwatts. So we can really put a huge amount of such devices on the chip. So here is the concept of the neuron. And so we wanted to demonstrate that the devices were good enough to indeed process some information, to do some neuromorphic computing task. So at the beginning, we didn't have a lot of experience and also a lot of devices. So we thought that we should try to demonstrate that we could use just one device, one nanoneuron, to demonstrate a neuromorphic task. And so, of course, with one neuron, you don't do much. It's not enough to do an interesting computation. So we use the trick that is called time multiplexing, actually using only one junction. We have emulated a neural network of 400 neurons. And we did that by using the junctions to imitate each neuron one after the other, right? So this is a time multiplexing. And what we did is that we used a neural network approach called reservoir computing that exploits complex transient dynamics in the device. And so in that case, the device was imitating the neurons and synapses were done on a computer. And what we have shown is that the nano oscillator junction could recognize spoken digits from 0 to 9 with a success rate over 99.6%. And why this number is important is because this is as good as software. So it shows that this nano device, that is very small, at room temperature, is stable enough, has low enough noise that it can compute with a high accuracy. So this was a kind of validation that we can use it as a nanoneuron. Then we wanted to show that indeed we could make some kind of neural network where neurons exchange microwaves. Okay, and so what we have done is that we have built a small 2-layer neural network. So here, in the first layer, we use, in fact, microwave equipment to emulate the first neurons. So these are 2 microwave sources that we bought. And the second layer here is composed of 4 nano oscillator junctions. And so these nano oscillators are connected electrically together, as you can see here. And as you remember, they emit microwaves, so we can look at their emission on the spectrum analyzer and check their microwave output. So what we did is that there is a strip line 300 nanometers above the oscillators, where we can send the signals coming from the first layers here, from the 2 microwave sources. And so what we wanted to show is that we could classify vowels. So we send we have a database of vowels where each vowel is characterized by a unique set of 2 frequencies. We send these frequencies into these microwave signals with this given frequency into the strip line. These signals create a microwave magnetic field on the junctions, and so their magnetization dynamics is perturbed, and so their emission is perturbed. And this is going to change their dynamics, and sometimes they are going to synchronize to the inputs. So what you see here, for example, is that this is the emission of oscillator 1, of oscillator 2, of oscillator 3, but the emission of oscillator 4 has disappeared because it has synchronized to the input B. And so this synchronization phenomena allowed us to classify the vowel. And we could do that with a high accuracy. And so what is important here in this case is that we showed experimentally that we could have a system of coupled oscillators, nano oscillators, magnetic tunnel junctions that could be trained to recognize signals, but also it was very important that we could actually communicate through radio frequencies. But what you may see is that here there is an important ingredient missing. There are no synapses, or let's say there are some synapses, but they are fixed, because what we are doing is that we collect the microwave signals from these neurons, and we send them directly into the strip line and apply them directly to the oscillator. We don't have some kind of elements here to tune the microwave signals impinging, coming on each neuron in the second layer. And this is very important to do that, because synapses and learning are really the power of neural network. So if we want to have state-of-the-art on-chip neural networks with nano devices like that, with these microwave neural networks, we need microwave synapses. We need elements, nano objects, that can modulate the incoming microwave signals. And even more, what we want to do is this multiply and accumulate operations that is typical, very important in neural network and typical of the synaptic operation, right? So we want to be able to perform this sum, to take the microwave inputs from the outputs from the oscillators, weight them, sum them, and then send them to the next oscillator. And so our idea actually was to use, again, magnetic tunnel junctions as synapses, but to use them in another mode. This time, they are not going to be auto oscillators, because we are not going to send them a DC input. They are going to be resonators, okay? So what's happening is that when you have a magnetic tunnel junction, it has a resonance frequency that depends on the material that you use, the geometry of the dot, many things. And you can tune it with this geometry, the material between maybe 10 megahertz and several dozens of gigahertz. And so when you inject a microwave current in a magnetic tunnel junction if the frequency of the incoming signal is close enough to the resonant frequency of the magnetization, then you are going to be able to excite this magnetization through the Ørsted field that is created or through spin torque. And so this is going to create a resonance. So what you are going to have is resistance oscillation at the same frequency as the input current that you inject. And the multiplication of these two sinusoidal signals is going to give rise to a rectified voltage across the junction, so a DC signal. So here you see some experiment. You see this DC voltage as a function of the frequency of the input. And here you have the resonant frequency. So because you are multiplying two sinusoids, it's not exactly the Lorentzian shape that you expect. So actually, when the magnetization here is oscillating at the maximum, you have a zero DC signal, and you have so it has this kind of special shape here. Okay, and so the resonant frequency of the junction in our case is about a little less than 300 megahertz. So what is very interesting is that this DC voltage depends on the amplitude of the input microwave signal. Actually, you see that if the input frequency, for example here, the input frequency of my signal is higher than the resonant frequency, when I send a small microwave power, I have a small response, small positive response, and the more I increase the microwave power, the more I go toward the red curve, and so the response increases. So you see that I'm multiplying the input microwave power with a positive weight. If I'm here at 250 megahertz, my input signal has a frequency that is lower than the resonant frequency. So here I have a negative response that increases when the microwave power increases. So I have a negative weight. So you see that I am, in this curve, able to weight the input signal, and that the weight is a function of the difference between the input frequency and the resonance frequency. So it means that I can tune this weight as I want to be able to do for a synapse. I can tune it by changing the resonant frequency of the junction. So there are different ways to change the resonant frequency of a junction. And in real devices in the future, probably the best way will be to do it using voltage-induced anisotropy modifications, which can be non-volatile. There are some recent papers on this. In our experiments here, just to demonstrate the concept, what we did is that because we have a strip line above the samples, we simply send a DC current through this strip line. This creates a magnetic field above the junctions that depend on the amplitude of the DC current. And this magnetic field is going to change the resonant frequency of the junction. So here you see how a DC current in the strip line is going indeed to change the resonant frequency of the junction. You see the shift of this curve here on the x-axis. Okay. And so what we plot here is the voltage as a function of the input microwave power for different values of the DC current, therefore for different values of the resonant frequency of the junction. And you see that the slope here goes from negative to positive, so we can have negative and positive weights. So this is really a synapse. Okay, so now we have one microwave synapse that takes microwave power as input and gives a direct voltage output that applies a weight on the input. And now we want to do this multiply and accumulate operation, the sum of this with several junctions. So how can we do that? For this, our idea is to use frequency multiplexing. So what we are going to do is that we are going to connect the synapses, synaptic junction in series, and we are going to allocate them different ranges on the frequency range. So you can see each junction as a resonator, as a filter that covers different frequency band. And we are going to decide that the microwave neurons also operate on different frequency ranges. So that each neuron, for example, this is the output of the first neuron, this one is going to talk only to this junction because its frequency range is going to correspond to this junction here, to this synapse. And this neuron will only communicate with this one because its frequency range is not here, it's only covered by this filter, and so on and so forth. And so if we do that, you see that since we have one-to-one communication between neurons and synapses, actually the voltage that we collect here across all the junctions, the direct voltage here is simply the sum of the weighted input powers by the different junctions. So we have a multiply and accumulate operation. What is interesting is that with only, let's say, one wire, we have here the 4 junctions in series, we can emulate this architecture where you see that we have 4 wires. Now, yes, and so we have demonstrated that experimentally with 2 junctions. We did that recently. So we did exactly what I described. So here we have the 2 junctions in series. You see here how we can tune the 2 synaptic weights. And we have demonstrated this multiply and accumulate operation. So here you see the ideal multiply and accumulate operation. Here the experimental measurement. And you see that we have the good trend with a bit of noise, but that in our simulation seems to be okay for computing. Okay, so this works experimentally. So now, if we want to make more complicated neural networks, for example, if we want to have 2 output neurons, what we can do is simply to add another chain of synapse for the second neuron. And the inputs to the 2 chains are the same. So here, with only 2 wires, we replace 8 wires. And so what we did is that we have shown through simulations that this can work. So here in these simulations, the inputs is a database of handwritten digits. Each pixel is converted into microwave power at a different frequencies. And because there are 10 written digits, you have 10 different, you have 10 synaptic chains, and so 10 output neurons. And what we did in this simulation is that we have emulated, we have not included the noise, but we have emulated really the specific shape of the spin diode effect and nonlinear effects. Here you see the simulation of the emitted voltage as a function of frequency. And so, and what we did is that we trained this network with the usual, with stochastic gradient descent, basically. And you see that taking into account the physics of the device, we can reach very high accuracy for recognition. So it proves that even if we have this shape that is a priori different from synapses in artificial neural networks, nevertheless, we can achieve very high classification. And so, of course, in the future, what we would like to do is to make large neural networks based on these microwave synapses and microwave neurons. And so you see that what is nice is that in our systems, the neurons, you remember, they take DC inputs and they emit a microwave power. And the synapses, they collect microwave powers and they rectify the voltage, so they output a DC voltage or a DC current that can then be fed into another layer of neurons and so on and so forth. And so we have, in that way, you see that we have the multiply and accumulate operation, then nonlinearity, etc., and that everything can connect together. And this is very important because it means that we can build some deep neural network, and this depth, this large number of layers, is very important to achieve a high quality of recognition, of classification, of accuracy. And so we are working on this now. Of course, we want to make a small demonstration at the beginning and then some chip. And so it's a work that combines physics, algorithms, and electronics. Okay, and so this is the first part of my talk on what we are doing in terms of spintronic nanodevices and why we believe that spintronics can, you see the physics of spintronics here can help for making neural networks here in the communication between the synapses and the neurons, but also through their dynamical properties that in the future we can even exploit more. How we can exploit it more, this is what I'm going to discuss now. I forget to say that we believe we can really gain a factor 100 in energy and speed up the computation by 100 compared to GPUs. Okay, so physics is interesting for the device, but I would like to show you now in the rest of my talk that using physics can also help for the learning algorithm. So why is that? Okay, so the flagship learning algorithm of deep neural network is called the backpropagation of errors. And what it does is that it minimizes the error at the output of the neural network. And so this is very important, and this is why it works so well. So today, backprop is what works the best for training neural networks. And so it's called supervised learning. So what you have is that you have a data set of training examples where you know the response that the output that the neural network should have. So you have the answer, right? So what you do is that how it works is that you take one of these inputs, for example, the image of a dog or a cat, put it here at the input of the neural network, and then you perform this successive operation, multiply and accumulate, nonlinearity, etc., until you get to the output of the neural network. Okay. And so you want, for example, the output to be a dog. So this neuron should say 1 and this one 0, let's say. Okay. And so at the beginning, the synapses are going to be random. So the output is going to be wrong compared to the output that you know. So you're going to have an error. And why backprop is so efficient? It's because it's going to correct each parameter, each synapse here in the network by its contribution to the error at the output. Okay, even if the synapses are buried deep in the network, they are going to correct their contribution to the error at the output. This is why it works so well. And how backprop does that? It's quite simple, but very mathematical. So you take the error as the output, and what you want is to compute this quantity for each synaptic weight. And so what you do is that you use the chain rule of derivatives to find these gradients. Okay. And so this works very well in software, but in hardware, it's quite complicated to do. Why is it? Well, this is because you need several circuits. Okay, so imagine you make a physical neural network. So you have your physical neural network, it's here. So you have first, you want to do the forward pass to compute the output. So you send the input, you inject the input here. you run all your computation in your physical neural network and you measure the output. So here you have the forward pass. But then you need to compute all these gradients. And for this, you cannot use this neural network. You need another neural network, or you need another circuit to compute all the gradients. And you need to store all these gradients in some additional memories. And there are many gradients, right? So you need huge memory. In addition to all your synapses, you need another memory. And once you have computed all these gradients and stored them in memory, you need another circuit to program each synapse according to the gradient, okay? And so it's another big circuit. And so it means that, you see, you have taken a lot of care to build this first neural network, but you need two other big complicated circuits. And so it's very complicated challenging to make these two other circuits energy efficient and very compact, miniaturized. Okay, so it's a huge challenge, and this is why today there are not really chips with nano devices that can perform state-of-the-art training with backprop. Although there are many, many people working on this. And so the question I'm asking is, can the physics of device help for this? So we know that nano device physics helps implementing the forward pass. So I gave an example in spintronics of how we can make a physical system that is going to emulate multiply and accumulate operation, nonlinear operation, multiply and accumulate, so on and so forth, through the physics of spintronics. Using devices that are called memory stores, that are actually multi-level nanoresistors, you can, using the laws of electricity, also perform the multiply and accumulate operation, and so you can also make this kind of deep neural networks. So, and that there are, of course, other examples. So nano device physics can help implement the forward pass. But can it help directly implementing training? Could it, remove the need of these two other complex circuits? And I think it can, and that the key is in an algorithm that is called equilibrium propagation, that was developed by Benjamin Cellier and Yoshua Bengio a few years ago. And so what I would like to show you in the rest of my talk is that with this algorithm, this algorithm removes the need to compute the gradients. Physics is going to compute the gradients for you. And then I will show you that it can also, in principle, remove the need of the third circuit to program each synapse. So what is this algorithm of equilibrium propagation? It's an algorithm that is really taking its roots in physics. So what's the difference with a traditional neural network? There are two main differences. The first one is that you see that it has the schematic is very similar, but synapses here are bidirectional, which means that the signals that propagate through the network can go in both directions. And the second very, very important point is that neurons are dynamical objects. So here, for example, in the original paper of ECPROP, they obey this equation. This dynamical system is described by an energy function, and each neuron dynamics is going to evolve depending on this energy. And of course, at equilibrium, everything is at rest, so every neuron doesn't move anymore. Okay, and so the idea of equilibrium propagation is the following. So you have these input neurons and you inject the input, and because you have a dynamical system now, and that is heavily connected where signals can propagate in every direction, it's going to be perturbed. So it's going to change and then evolve and then go at equilibrium. Okay. And then you can measure an output. Now, if this output is not correct, the idea of ECPROP is to try to bring the network closer to the value that you would like it to have. And for that, the idea is simple. It says, well, all you have to do is apply some kind of spring-like force on your output neurons to nudge them towards the output you would like to have. And so when you do that, you see that you modify the dynamics of the output neurons to bring them closer to where you want. And of course, this dynamic is going to modify these neurons here and so on and so forth, because signals propagate in all directions. And so there is going to be a perturbation. Then after a while, the system is going again to go to equilibrium. All right. And so what's happening here is that you, by nudging the output in that way, somehow you have propagated gradients through the network. And so basically, this new equilibrium is closer to what you would like for your neural network. And so what you would like is to be closer to this configuration and less close to this one. And so equilibrium propagation says that, in fact, you just need to adjust each synaptic weight according to this learning rule here. All you have to do is to measure the activity of neurons after this first phase and measure the activity of neurons after this phase and apply this rule and subtract here, okay? This somehow means that you are stabilizing this one more compared to this one. And so you see that what is very interesting is that all you have to do to compute the gradients is just to measure the activity of the neurons at equilibrium, their frequency, let's say. And then the gradients are computed, so you didn't need to do all this complex numerical differentiation, and then you need the third circuit to write the synapses. And so some results that we had recently in collaboration with the team of Yoshua Benjo is that we have shown that there is a mathematical equivalence of this algorithm, this simple algorithm, with the gradients of backpropagation through time, which means that equilibrium propagation is equivalent to stochastic gradient descent, so that you can have, in principle, a high accuracy of training. Now, in these systems, when you simulate them, so this is when you simulate them on a GPU, you need to solve all the differential equations of this very complex system. So this simulation takes a lot of time. So it's very difficult to scale them to the large image benchmark of today, like ImageNet. Nevertheless, recently we have shown that it can scale to an important task, image recognition task that is called Cypher-10. Okay, so it works on challenging benchmarks. Now, in the original version of ECPROP, you still need an external circuit to write all the synapses. But what we have shown also with the team of Yoshua Benjo is that actually you can write the synapse while you nudge them if you follow this rule that is adapted from the other one. And so this made us think, well, maybe we could remove this external circuit, and maybe, just like in the brain, we could use spiking neurons and use the voltages emitted by the neurons to write directly, to program, to modify the synapses during this nudging phase, while the gradients propagate and are encoded into the spikes of the neurons. We could directly use these neuron spikes to write the synapses. And so in this recent paper here, we have proposed simulations. We have proposed a circuit that we have simulated, that where the neuron activity, the neuron spikes directly write synapses. And so it's a very simple circuit that can be done with standard electronics. And so it's a spiky neural network adaptation of equilibrium propagation. And so we have shown through simulations that it achieves state-of-the-art for online training in spiking neural network. And we believe that it opens really the path to making on-chip neural network that learn intrinsically, because all you need to do is to apply your inputs, nudge the output of your physical neural network, so modify a bit the output, and then the gradients are going to be computed directly by the dynamics of the system, and the spikes of the neurons are going to write directly your synapses. And so you don't need other circuits. The system is independent, it learns intrinsically. And so we think this is the road to low energy neuromorphic computing, at least one possible road. And so we have made different advances recently, mostly through simulations. Something we have shown also is that actually binary synapse can also work in this case, only two states, even if the gradients need to be real. This is very good because this means that this is quite tolerant to device faults. So, but you see that here, this algorithm really exploits dynamics and physics of systems and possibly nano device to learn. It really is going to learn just like a ball rolls down in a potential well. So this is also satisfying because this is quite elegant. Okay, and so what I hope I have shown you in this talk is that neuromorphic computing is a very exciting field where there is a lot of work because you need to tackle at the same time the nano device, materials, and the algorithms. And this is also what makes it very exciting. Thank you.
Thank you, Julie. Thank you for this very exciting, very nice talk. We are receiving questions now. People can ask questions either by raising your hand at the Zoom platform, or you can write the question directly here at the chat, or I will receive questions from YouTube as well. I have a question, a very basic one, I think. You mentioned spintronics as one of the possible platforms for emulating a neural network, and you mentioned that there are other platforms as well. Is there a good figure of merit to compare different platforms, and how do they, let's say, how do they rank nowadays in terms of which one is more advanced?
Yes, so it's a very good question and very difficult to say also because it's not like there are some existing systems right now. So the systems that is the most studied, are resistive switching oxide for memory stores, complemented with CMOS or phase change memories. But now there are more and more works on spintronics. It's very difficult because when you look roughly at the figures for energy consumption, speed, everything is a bit equivalent. So it's going more to be a link, I think, to device faults and how algorithm can be adapted to these devices and robustness. So it's hard to say, and so that's why I think many industries are keeping up on the different technologies, because it's difficult to say if there is going to be, it's like for the memory, in fact, it's not sure that there will be a winner, but it could be that each branch of materials has different advantages.
All right, thank you. We have a question from Mauricio Pires. Mauricio, you can ask your question.
Hello, nice to see you. I enjoyed very much your talk. Very happy that I could be here to see it. I grow with semiconductor MOCVD growth, and I'm used to grow quantum dots, self-organized quantum dots. And looking to your scheme, I was just thinking if to teach a specific system something, right? And well, what I was, obviously I'm not on this area, so it was very, very nice to see you talking. But it seems to me that actually it's a question, is there something going towards some biased, self-organized system that you could, meanwhile it's growing, you could try to put some input, and afterwards it would try to see if that could go to a specific answer that you would like to have. Is there something in that direction being made?
In your question, when you, I think I'm not sure, you use the word growth, so you mean a system that can grow?
Yeah. What I do is MOCVD, semiconductor epitaxial growth. That's what I do. Quantum dot, for example. Mm-hmm. And you can do this self-organized quantum dot, so that you just they just grow. You discover some nice condition thermodynamically that they grow by itself. Mm-hmm. And it seems that this type of solution, if you have these specific neurons, that you could bias them in a certain way to respond to a certain growth, that could be something that could try to teach them to have a specific answer. Just curious if there's something being done in that way.
It could be the difficulty I see that it's interesting, but you would need to be, so like when you train on images or things like that, you need to show millions of examples. So somehow you would need a way to, that during the growth that you could modify the system while it grows, but many times. You see each time.
Yeah, obviously I'm asking some very, very much easier question than identifying the image. Maybe only very simple inputs. But I enjoyed very much your talk. Thank you very much.
Thank you.
Okay, well, we have a couple of questions from YouTube. Let me go to the YouTube and ask a question from YouTube. A question from Ismael. Let's say I implement a back propagation algorithm in my computer at home today. What would be the difference if I implement the same algorithm in an architecture where each neuron is a tunnel junction? Maybe you understood the question better than I did.
Yes. So I think again, in the hypothesis that we can make the same neural network, which is not the case right now, but if it was working, we expect that because we colocalize memory and processing, we could gain at least a factor 100 on the energy that it would require to run and to be trained, and also speed up by 100. So that's the whole, really the whole motivation for neuromorphic computing is trying to minimize the energy consumption. And this is also why in the second part of my talk, I was, trying to show why we don't want to have too many circuits on a chip, because each time you make a new circuit, you consume energy. And so that's why you want to have the minimal system that allows you to do that.
Okay, thank you. Thank you, Ismael, for your question. There's a question here from the chat from Luis Gregorio Diaz. In the nano device, can you play with different activation functions and hyperparameters of the neural network? And he congratulates you for the very nice talk.
Thank you. So Well, so of course, a hardware neural network will always be a bit fixed. So for the, I mean, if we want to do a hyperparameter search, we would probably need to make a larger neural network than to be sure that we can choose the structure. And for the different activation functions, we could, the activation function of a magnetic tunnel junction, for example, is going to depend on the applied fields, things like that. So we could possibly have additional levers to change it, but the more tunable parameters you have, the more energy consuming it will be, I guess. So there will always be some trade-off with flexibility.
All right. Thank you. Thank you, Luis. Let me go back to YouTube. There's a comment and a question from Gilberto Ribeiro. Very exciting results concerning the magnetic tunnel junctions. I understood that the neurons would be broadcasting, so to speak, in order to implement the synapses with different weights. So my question is about scalability. How can you achieve 10 to the 4 different synapses? I'm not sure if you could achieve a large number. Your thoughts are most welcome.
Yes, so what we estimate in that theoretically well, first maybe what I should say is that in today's neural networks, there are no more than 100 synapses per neuron. We are far from the brain connectivity, and in part because of the restrictions of our computers, they cannot do it. So we have calculated that in principle, we can have chains of 500 junctions with 500 different frequencies, okay? But if we want to have more synapses per neuron, we can repeat these chains. And so we think we could that way go to a few thousand.
Okay, thank you, Gilberto. There's a question here at the chat from Davi Rodrigues. Actually, 2 questions. First question, since you are using ferromagnetic systems, is there a possibility to gain from stray field coupling between the MTJs? Or is the stray field disruptive to the system?
Okay, so if we want to make an equivalent of backpropagation, the stray field is going to be more an issue than a solution, because in standard neural networks, there are no connections inside a layer between the neurons, so you don't want them to feel each other, basically. However, in the brain, there are connections inside the layer between the neurons, and so maybe in the future we could use that, but it's not clear how. So again, this would be some kind of thinking on the algorithm and the device physics, and that's interesting.
I see. And there's a second question from him. These MTJs at DC voltage may easily heat up. What would be the temperature efficiency of the device? Moreover, would this change in temperature be disruptive to the device as well?
Okay, so, yes, they heat up a bit, but not so much, actually. We use these magnetic tunnel junctions. They don't heat that much. And so we use them, at room temperature with the varying temperatures of our room. And so we have no problem. So now, of course, if you start them to put them in a car close to the engine, I think you could have indeed some issues. But yeah, we didn't study that in detail. But okay, I think it works in a normal environment.
All right, thank you, Davi. And there is one question here from Antonio Azevedo. How far are we from spintronic neuromorphic device being competitive? And he apologizes because he doesn't have a microphone at the moment.
So again, it's difficult to say what means competitive. Competitive towards the GPU, we are very, very far, but all other hardware I mean, are very far from being yet competitive with the GPU, because the difficulty is really there are two difficulties. There are three difficulties. You need to make this huge number of synapses and neurons, connect them together. So you need really, hundreds of millions. You need to connect them together. You need to train them. So that they, and also you need to have an accuracy that matches what CMOS can do. And so this is difficult. They are certainly competitive compared to other emerging memory technologies, for sure. And they have a lot of interesting functionalities that the other emerging memory do not have, like, for example, this microwave emission. But yes, there is still a lot of work toward making a real system.
Thank you, Antonio. And I think there is a final question here from Leandro Mercedes. Thank you, Julie, for this very nice talk. Question: considering 100 nanometer square cross-sectional area magnetic tunnel junction, what would be the role of the magnetic domain walls in the system's spin polarized current injection efficiency?
I see. Yes. So I think you ask these questions because we have in our experiments used nano device with this kind of diameter, larger diameter even, and in our case, we were using vortex textures. So. And so in that case, we have a very nice oscillator, but it's true that you certainly would want to control your texture so that you don't have some uncontrolled domain wall in the middle of your dot, etc. But if you make an ellipse of 100 nanometer with a thin enough magnetic layer, you're going to be macro spin-like behavior with a bit of edge modes, but so there are ways to tune the geometry to avoid this, I think.
All right, thank you, Leandro. And I don't see any other questions right now. So as we usually do, I would like to ask everyone to open their microphones and thank Professor Julie Grollier for this very nice talk. For accepting our invitation to speak to us. And thank you, Julie.
Thank you very much for listening.
Thank you. Yeah, I will stop broadcasting YouTube right now. Okay, we're